Welcome you all in my next lecture. So this lecture onwards I will talk about concept of partial derivatives, directional derivatives, tangent plane, normal line of a surface, total derivative, chain rule and higher order partial derivatives. If you remember, in my last couple of lectures I talked about like functions from Rn to Rm, then the concept of convergence of sequences, then the concept of limits and continuity. And as I said, now I think I should talk about the concept of differentiability for a functions f from Rn to Rm. So now next couple of lectures I will talk about like the concept of differentiability for functions from Rn to Rm. And while talking about the concept of differentiability, the concept called like partial derivatives, directional derivatives and the tangent plane, normal line of a surface, and then total derivative, chain rule and higher order partial derivatives, that will automatically come. So our main objective is to learn those concepts in couple of lectures. So let me start with those concepts. Okay. So now I want to talk about the differential calculus, I mean the concept of differentiability for functions from Rn to Rm. Okay. So now if you remember, what are the functions I have defined, like functions from Rn to Rm. So you can partition those functions into three parts. So like task, extend the differential calculus for those class of functions or those sort of functions. What are the functions? Case 1. Case 1 means it is a functions from set of real numbers to Rn. That means it is a vector valued functions of real variable, case 1. What about case 2? Case 2, it's mapped from domain Rn to range R. That means it's a real valued functions of vector variable. And the third one is that it's a vector valued functions of vector variable. So that means I have somehow partitions my class of functions from Rn to Rm into three parts. One is the vector valued functions of real variable. Second one is that real valued functions of vector variable, and third one is that vector valued functions of vector variable. So now I will discuss the concept of differentiability in three cases, and you will realize that the case 1, when I am going to talk about the concept of differentiability, you will see the notions of differentiability in the real variable case, you can just immediately extend those concepts. Whereas when I will talk about the concept of differentiability in case 2, that means I have a real valued functions of vector variable, then you will see the concept of differentiability in the real line will not kind of easily extend, because the notions of divisions will not make sense in context of real valued functions of vector variable. And of course case 3 will have the similar sort of difficulties we will face, because it's like case 2 is a special case of case 3. So yeah, so that's the questions I have written. So what does it mean to say that f is differentiable in case when my functions f is from Rn to Rm? Let's see. So case by case, let's see. First let's talk about like case 1 case. How do I have the notions of differentiability of vector valued functions of real variable? Okay. So before that, let me just give some kind of examples. I already talked about that, but again just before that, before giving the notions of differentiability, let me just give some couple of examples of vector valued functions of real variable. In particular, I will focus on n is equal to 2, n is equal to 3, because in that case we will have the picture. Okay. Okay. So for example, first one. So vector valued functions of real variable. Okay. So vector valued functions means my range is R2 and domain is R. So let f from R to R2 is a functions. How do I define it? It's f of t is equal to t comma t square, where t is running over the full real line R. And now if I cap, these are standard notations 1 comma 0 and j cap is 0 comma 1 are the standard orthonormal basis in R2. So that means you have a R2 two-dimensional plane, you have 1 0 0 1, that forms an orthonormal basis. I denote I cap, this is 1 0 and j cap is the 0 1. So then what will be my functions? If I write this is the functions from R2 to R2, I can write in terms of I can and j cap is t times I cap plus t square times j cap. Okay, because t times I cap is actually, if I hit it by t times 1 comma 0, it is t comma 0, and t square times, so that if I write it t comma 1 0 plus t square times 0 1. So you just multiple, scalar multiple. Okay, so this should be t comma 0 plus this should be 0 comma t square. You add it, this is t comma t square, and which is nothing but this. Okay. So now I have a functions ft from t times I cap plus t square times g cap. So now you can draw a picture there. And what is this? So we can now depict a vector valued functions f from R to R2 by drawing only its range. So that means range means what? If I take t from some real number, what will be ft? Ft is a point in R2. So therefore, at t varies from R, it will kind of have a picture. And what is it? That's what I have written. If you think ft as a point in the xy plane, then as t increases, ft traces out a curve C in the plane. And if you draw it, it will give you some picture. In this case, what will happen? If I draw the arrow of the curve indicating the directions in which the curve is traced out as t increases. So that means t is a function from a whole R. So that means if I come back from these directions, minus infinity to plus infinity, that means it will give you this. So I have put a arrow mark. So it will give you this kind of curve. And this is nothing but, if you remember from your geometry, this is nothing but a parabola. So in other words, if I write it an x and y coordinate, what is my x? X is equal to t and y is equal to what? T square, that means x square, and you know what is the curve y is equal to x square in the two-dimensional plane. It is nothing but a parabola. Okay. So this is one example. So now the another kind of concept you all are familiar with that. What is that? That is called parametric equations of a curve or parametric curves. So that means if I have a curve in R2 and R3, it will have a parametric representations. Okay. So before that, I need to explain what do I mean by parametric curves or parametric representation. So this is the definitions first I have given. So a curve gamma in Rn, okay, is a continuous function f from the set I, which is subset of real line, to Rn. So that means if I have a curve in Rn, so what is the definition I am giving? I am saying that a curve gamma in Rn is a continuous function from where? Its domain is some subset of real line to Rn, where I is an interval in R. In other words, I have written, in other words, we say that the curve gamma is parameterized by the functions ft. So that means if I have a continuous functions capital F or some f from the set I, which is subset of real line to Rn. Okay. So now if I draw this curve, the graph of ft in R2 or Rn, of course Rn is difficult. So but you will see later, I will give some examples. If I draw, then it will, I will say that it becomes a curve in Rn because the functions taking values in Rn, and the corresponding functions f is nothing but the parameterizations of the curve gamma. Okay. In particular, that means in particular, if I take Rn is equal to R2 and if I consider the functions ft, which is nothing but, since it will have two components, right, I cap and j cap, because I am in R2, it will have a basis 1001, I cap and j cap, that I already discussed in my last slides. So this is nothing but f1 I cap plus f2 g cap. Okay. So this can be written as, because I am in R2. So now rewrite it in different notations, right? For example, in R2, I can also define in terms of Cartesian coordinate x and y. So that's I have written. So x is equal to x2. In this case, it is nothing but f1 of t. Y is equal to f2 is exactly equal to f2 of t in this case, for t is running over I is a subset of R. Now the set of equations x is equal to xt and y is equal to yt as t running over I, where x and t are continuous functions on I, is called the parametric equations of the curve. Right. So that means if I have a functions capital F from some subset I R to R2, then it will have two components, right? So I have written f is equal to f1t I cap plus f2t j cap, right? Now in terms of Cartesian representation, you know this will have a representation ft is equal to xt comma yt. Okay. And in this case, what is my xt? Xt is f1t, yt is f2t. Now if you remember when I was talking about the continuous functions from R to Rm, if you remember that if I each functions has a component wise representations, and the continuity of the original function implies the continuity of the component functions. Similar thing is going on here. See, this is the corresponding component functions. Capital F is continuous given. So therefore xt and yt in this case also continuous. In our case, xt is nothing but f1t, yt is nothing but f2t. So that's how I have written. So the set of equations x is equal to xt, y is equal to yt, where xt and yt are continuous functions because capital F is continuous. Those the component functions are also continuous functions, is called the parametric equations of the curve. Some example, let's see. Okay. So that means if I have a curve in Rn, it will have a parameterization. And what is that parameterization? It is a continuous function from some interval I subset of R to Rn, where I am talking about the curve in Rn. Okay, so but it might happen that a curve may have a different parameterization. It is not unique. That means if you have a curve, you will have kind of various, like you will have like different sort of parameterization. So not like it will have a unique parameterization. For example, look at these examples. Okay, so let's take xt is equal to t and yt is equal to t square. Okay, so now once we have this xt is equal to t and yt is equal to t square, then you can immediately say that this is nothing but the representation of the parametric representation of the parabola, because this is the relation y is equal to x square and this is a parabola, right? So now I am changing my function xt and yt in this way. So now if I take x star t is equal to t minus 1 and y star t is equal to t minus 1 square, t minus 1 whole square, where t running between r, t runs over full r, then also you will say that continuous functions, that means the functions ft whose component is xt comma yt. Okay, so it will give a curve, and that curve is same as the parabola coming from same parabola it will give. So that means a parabola, if I take in R2, it will have various parameterization. One is xt is equal to t, yt is equal to t square. Another one is x star t is equal to t minus 1, y star t is equal to t minus 1 whole square. So in other words, you can kind of club everything. So you can say that for each real constant c, if I consider xct is equal to t minus c and yct is equal to t minus c whole square, that is also a parameterization of the parabola y is equal to x square. So that means the parabola has various parameterizations, so it will not unique. Okay. Okay, so that is another kind of parameterization. So it is an ellipse. You can see by looking at the picture, this is an ellipse. So it's I have written here the parametric equations. Like if I have the parametric equations, that means if I have the first component, again I am in 2-dimensional case. So that means my functions is f is a map from 0 to 2 pi, which is subset of r to r2. Okay, and what is my component ft, which is equal to xt, okay, comma yt. So this is my function, and xt is given here and yt is given here. So if I have that parameterizations, then if I draw a picture, so that means for fixed t, if I take the point ft, which is be a point in R2, and t running from 0 to 2 pi, that means if I t is equal to 0, it will give some point. For t is equal to 0, what point it will give? It will give cos 0 is equal to 1. That means for t is equal to 0, the point you will get is equal to 6, 0. Okay, so that's all. So that means 6, 0 means what? This is the point. Okay, this is the point. So now as t running from 0 to 2 pi, that means it's taking 0 and then going through 2 pi, then it will trace out this path. And t is equal to 2 pi, it will be the same point. So it will be an ellipse. So therefore, this is the corresponding parametric representation of an ellipse. Okay, so this I have seen the kind of curve in R2. Now if I am in R3, that means vector valued R3 functions of real variable. Similar sort of definitions will be there, but only in R3 we know it will have a basis of 3 vectors. Like earlier in R2 you had 2 orthonormal bases, now you will have the kind of orthonormal basis consisting of 3 vectors. Okay, so what are the vectors? So I am denoting as I cap is 1 0 0, j cap is 0 1 0, k cap is 0 0 1. So R3 has a basis consisting of 3 orthonormal vectors. I am denoting as I cap, j cap and k cap. So therefore the functions f can be defined as ft is equal to f1t, f2t, f3. This is nothing but the component functions, and if I write it, capital is in this form. So that means f1t times I cap plus f2t times j cap plus f3t times k cap. Now if ft is continuous, capital Ft is, that means original function is continuous in the interval I, then it traces out a curve in R3 because its range is in R3 as t varies over I. And we can rewrite these parametric equations, of course, as in earlier, because this is nothing but the component x, y, z. If I write it as ft as xt, comma yt, comma zt, then your xt is nothing but f1t, yt is nothing but f2t, and zt is nothing but f3t. And if capital F is continuous, f1t, f2t, f3 are continuous functions, corresponding xt, y to zt are continuous functions. So therefore, if t varies in I, for each t it will give you a point in R3, so you can trace out a curve. So that is the corresponding parametric representation of a curve in R3. Okay, I have given an example of a curve in R3. So this is like if I take the parametric representation, xt is cosine t, yt is equal to sine t, and zt is equal to t. So that means what is my function? My function is capital Ft. So it's nothing but xt, yt, and zt. That means capital F is a function from where? 0 to 4 pi to R3. That means for each t, ft is a point in R3. Now, if I take t is equal to 0, then what is my f0? So, if I take f is equal to 0, so that means f0 is the cosine 0 is 1, sine 0 is 0 and 0 1 0 0. So, that means I am starting with this point. And as t increases from 0 to 4 pi, so it will be like that. This is the direction I have given. So, this is called a circular helix in R3. So, if I have this parameterization, it will give a curve, and that curve in R3 is nothing but the circular helix. Okay, so at least we have some idea what kind of definition of curve in R2, R3 in general Rn, and what will be if I have a parameterizations, then how kind of one can draw a curve. So, okay, very special cases we know. So, that means a curve is a continuum of functions from some interval I subset of R to Rn, and if I have R to R3, then you will have, I given special examples, and you can draw it and you can have various curves there. So, now once I have the notion of curve or functions in Rn, then I now like to kind of give the notions of differentiability. That's why I have written differentiation of vector valued functions of real variable. That means my function domain is R and range is in Rn. Okay. Special case n is equal to 2 and n is equal to 3 I will discuss. Okay. Now, you will see, as I said, that the concept of notions of differentiability for this sort of functions actually similar to the definitions that you familiar with in the derivative of a function from real variable to real variable. Because if you remember the definitions of real valued functions of real variable, then what is the definition? Suppose if I have a functions from R to R, so what is my definitions? Suppose my function is nice and it is differentiable at the point some, say t naught. So, what is my definition? This is limit t approaches to t naught ft minus ft naught divided by t minus t naught. So, that we know, right. Now, you see that similar sort of definitions I can give, because like in this case for functions from R to R, so ft is a real number, ft naught is a real number. Now, I can divide by t minus t naught. That makes sense, right, from real to real. Now, same set of definition or same kind of definition I can bring it to the case from functions of R to Rn. Why? Because I will put the same definitions that I have given, you see. So, let us start with the function f from some subset S of R to Rn, where I am just assuming that S is an open set. Okay, I have already discussed what do I mean by open sets in Rn also, R you know. So, suppose S is an open set in R, define a function f, let t naught is a point in S. I will say that the function capital F is differentiable at a point t naught if this limit exists. What is that limit? So, that means similar sort of like in the real kind of real setting we will have it. So, that means what I am doing is that consider the quotient. Of course, one can say that, well, does the quotient make sense? Answer is yes in this case. Why? Because capital Ft is a vector in Rn. Capital Ft naught is a vector in Rn. So, Ft minus Ft naught is a vector in Rn. Now, I am just hitting that Ft minus Ft naught by 1 by t minus 2, and that makes sense because t is a real number, t naught is a real number. So, 1 by t minus t naught is a real number, and you can hit some real number with some component, right. Ft minus Ft naught is a vector in Rn, and you can multiply with a scalar. It forms a vector space I already discussed. So, therefore, that it makes sense because since I am dealing with the functions from R to Rn. So, therefore, this quotients perfectly makes sense. So, now we just bring the definitions that you are kind of with R, you know the definitions like the limit of that quotient Ft minus Ft naught divided by t minus t naught exists. Same thing, but only thing is different is that earlier you will have Ft minus Ft naught divided by t minus t naught is a real number. Now, we will have Ft minus Ft naught divided by t minus t naught is a vector in Rn. But we know that concept of limit in from functions from Rn to Rm, we know. So, what you have to do? Same definition will be there. Instead of mod, it will have just the norm. That's it. So, that means everything will be same, except you have to consider the existence of limit in terms of norm in Rn, because this time this quotient is a vector in Rn. That's it. Okay. So, that is the definition. So, if I have a function f from a subset of R to Rn, I will say that my function capital F is differentiable at the point t naught provided this limit exists. Okay, I have written in this case we say that if suppose the limit is exist, capital F is derivative at the point t naught, and we will say that derivative of f at the point t naught is nothing but this limit. Clear? Okay. So, therefore, there is similar definitions like in R, you know, real valued functions of real variable. You can have it here itself, because here the quotients perfectly make sense, and you can take the limit in Rn in the norm of Rn. that I already discussed in my last couple of lectures. So the Leibniz notations, this is the corresponding notations. I will say that derivative is nothing but df dt. Well, I am just giving a kind of again saying that an open sets. Yeah, I already maybe I discussed in my last couple of lectures, last lectures when I talked about open sets, because I have started with the definitions capital F from an open set. So, but you can start with an open interval, that's also. So, that is what I am saying, an open set S in R will be an open interval or union of finite or countable number of disjoint open intervals. So, therefore, many books you will see it started with the definitions of open interval, but the more generally you can start with the definitions from open sets, because open set is nothing but open interval or countable union of disjoint open set is countable number of disjoint open intervals, so or finite, so whatever it is. So, therefore, you can start with open interval as well. Okay, just very simple examples. Okay, so consider the functions capital F. Okay, this is the functions from where to where? This is a functions from R to R3. Okay, and how it defines? So, f of t is nothing but, okay, I have written here. So, this is t 2 and t square. In other words, what are the component functions? As I said, if I have a functions from R to R3, then it will have 3 component functions. What are the component functions? If I write it, say f1t, f2t and f3t, where f1 is a functions from R to R, f2 is a functions from R to R, and f3 is a functions from R to R. And very simple function, f1t is equal to t, f2t is equal to 2, and f3t is equal to t square. Well, the questions you can ask, right? For example, the concept of limit and continuity, there is a relations between the existence of limit and continuity of the original functions with the component functions. In that case, what will happen? That I will discuss in within 1 or 2, 3 slides. I will discuss that one. Let me just see the examples. Okay, so this is my functions capital F t comma 2 comma t square for t belongs to R. Then you can check the differentiability from the just definitions. What you have to do, you just consider the quotient, as I already discussed. Quotient perfectly makes sense. Okay, so that means ft, I am just writing in this way. So, this is ft means t comma 2 comma t square, t naught 2 comma t naught square, because at the point t naught I am talking about the differentiability, divided by t minus t naught. Then just by vector additions and scalar multiplications, you can have this component. First component, you can just combine these two, you will have this. Then again you can mix in the component again by additions and scalar multiplication. So, first component will be t minus t naught divided by t minus t naught. This is 0, this is this one. And of course, you know, if the existence of limit and component functions, there is a relations. So, therefore, this is nothing but I can say that limit of t approaches to t naught, t minus t naught divided by t minus t naught. This is you can do easily. So, first one what will give is the limit is 1, second one is 0, and third one is t2 naught. So, therefore, this function capital F is differentiable at the point t naught, and derivative of f at the point t naught is nothing but 1 comma 0 comma 2 t naught. Very simple example, just use the definitions, it will get it. Okay, so now in the real variable case, like functions of real valued functions of real variable, there is a geometric interpretations. The similar kind of things you can talk about in case of a functions from R to Rn. Okay, that's I have just tried to explain. So, denote C is the curve traced out by the functions. So, if you have the functions capital F from R to Rn or R, so that means then the corresponding there is a curve, as I said. Okay, so let denote C is the curve traced out by F. So, let P and P naught be a points on C corresponding to Ft and Ft naught. So, if I have a T, so Ft will give you a point. Let I am saying this is a capital P, and Ft naught for T naught, then you will have a point P naught. So, for example, look at this one. So, this is my T naught. So, that means this is my point f of T naught, which is nothing but I am giving this is P naught. This is the P naught point, this is the P naught point, okay, and this is the corresponding P point. So, I have a functions f from say R2, I have of course R2 or R3. So, that means I will have a curve, and the corresponding point T I am giving the point P Ft, and this is the Ft naught, not an issue. So, then what I am saying is that if I take the difference Ft minus Ft naught has the same directions as the second vector P naught P. So, that means this is my vector P naught P, this is the vector P naught P. Okay. So, this Ft minus Ft naught has the same directions as the second vector P naught P. Now, if T is greater than T naught, then ft minus ft naught divided by t minus t naught. So now if t is greater than t naught, t minus t naught is positive. So therefore ft minus ft naught divided by t minus t naught have the same direction as the vector p naught p, whereas if I take t is less than t naught, of course it will have the opposite directions, because it will have t minus t naught will be negative. So it is, in other words, it is the direction of p naught instead of p naught p. Therefore, so if suppose the derivative at the point t naught exists, then what is going on? So if I have ft naught, right? So that means if I have the corresponding second vector, right? So this is the vector p naught. So then what will happen, as t approaches to t naught, you see that second p naught p, it becomes a tangent at the point p naught. That exactly going on. That's what I've written. If f prime t naught exists, it is the limit of vectors parallel to the second vectors passing through p and pointing in the same general directions in which c is traced out by f. And it is reasonable to say. So therefore, so that means what? So that means I have a vector p naught fixed. So because I want to talk about the differentiability of f at the point t naught. So what you do? You take the f t naught point, that is p naught. Consider any other point t. So let it be ft. Action of f of the point t is ft, which is p. So you have a vector p naught and p. Now, what is the definitions of derivative at the point t naught? It's like about ft minus ft naught divided by t minus t naught, and while t approaching to t naught. So now then we have seen that directions or second vector, the directions of the vector p naught p and the directions of ft minus ft naught divided by t minus t naught has the same direction. That means if t approaches to t naught, then the corresponding vector p, which is nothing but f of t, which is goes to p naught at t naught. So that means the kind of, I should say, the second vector p naught p, if the derivative exists, it is nothing but the tangent at the point t naught. So that's what it is going. That's what I have written. So it is reasonable to say that f prime t naught is the tangent to c at p naught, if the derivative exists. Because so if I have any point p, it is nothing but the second vector, right? And while t approaching to t naught, it becomes a tangent. So like in the real variable case. Well, so that's the kind of relation, as I said. That means, is there any relations between the existence of differentiability and the component functions? Okay, look, so I have written relations between derivative of capital F and derivatives of its component functions. What is this? So let capital F S from R to Rn, where S is an open set. Once I have a functions R to Rn, it will have a component representation of component functions. This is f1t, f2t and fnt. So now let t naught be a point in S, then this theorem one can prove it, and this is a kind of theorem you can say. So you say that if capital F, the original function, is differentiable at the point t naught if and only if each of the component functions fi is differentiable. Each of the component function fi is a function from where to where? It's a function from R to R, and that differentiability, concept of differentiability, you are familiar with. So therefore, the concept of differentiability of the original functions f from R to Rn, you can have a relations between the concept of differentiability of the component functions. And in real case, you know, if my function is differentiable, it is continuous function. So therefore, in this case also similar sort of things you should expect true. And answer is, of course, it is indeed the true case. That means if capital F is differentiable, then capital F is continuous. Okay. So I am not going to prove that theorem, but it is, in fact, you can prove it. You just use the definitions of differentiability. Use the definitions of differentiability, that means existence of the limit of the quotients. Use the definitions of the existence of limit, that means it use the definitions of norm of Rn, and using the definition of Euclidean norm of Rn, you will be able to show that the existence of derivative of the component function is equivalent to the existence of the derivative of the original function. Okay, some kind of applications, that means the example I have given. So take this kind of functions. It's a functions from R to R3, right? What are the component functions? You can easily identify the component functions. So first component function f1t is equal to t, whose derivative is 1, you know. Second component function f2t is equal to 2, is a constant function, derivative is 0. Third component function is t square, whose derivative is 2t. Okay. So therefore, you can easily say by earlier theorem, each of the component function is differentiable. Therefore, my original function is differentiable, and not only that, you can talk about the derivative. So therefore, you can, by theorem mentions it is differentiable, and derivative is nothing but f1 prime t, f2 prime t, f3 prime t, which is nothing but 1, 0, 2t. Of course, the first principle, like the using the definitions, you can prove it, but this is another way. Once you identify the component functions, and you know it is, you can easily do the differentiation from real variable function of real variable. then the original function's differentiability you can talk about. Let's see another example that you cannot have the differentiability. Okay, so I have a function capital F which is mod t2 comma t square. Again, I'm just asking that check the differentiability. Again, you can easily identify what are the component functions. So first component function is modulus functions. Okay, second component function is the constant function 2. Third component is t square. So second and third component function is very nice, right? You can differentiability is there. But what about the first component functions? First component function is the modulus functions. But what I know about the differential with the modulus functions, and it is very straightforward. We know that these functions f1 is differentiable everywhere except at the point 0. Okay, so I have written since f1 is not differentiable at the point 0, so therefore I cannot say that capital F is differentiable, because capital F is differentiable if and only if all component functions. So I have f2 and f3, these are very nice. So f2 function, what is the f2 function? This is 2, and what is f3? This is t square. So these are very t square, sorry. So these are very nice functions, these are differentiable, but the functions f1, the first component function, which is not differentiable at the point 0. So therefore I say that the capital F, which is a function whose component functions are f1, f2, f3, which is not differentiable in whole R, rather it is differentiable in R minus 0, because I know the component functions f1 which is differentiable everywhere except the point 0. So therefore this is differentiable in R minus 0 except the 0 point, and you can also have the derivative is 1 0 comma 2t if t is positive, and it is minus 1 0 2t if t is negative. But it is not differentiable on whole R, because the first component function is not differentiable at the point 0. Another example, so take a function capital G which is if t running over a set of rationals, it is 1 comma 2 comma t square, and if t runs over irrationals, I mean R minus q, this is set of all rationals. Set of all rationals, rational point, RATI or NAL, rational points, and this is irrational, complement of rational. Then one can talk about the differentiability of this kind of functions. Again, you just look at the functions. What are the component functions? You can easily identify the component functions. So first component functions of G, say let it be G1, G2 and G3. Suppose this is the 3 component function. So let it be Gt, G2. Now what is G2 and G3? You can say that G2t is nothing but constant function 2, of course, by definitions, because it is 2 if it is rational, again it is 2 for irrational, that means it is 2 for whole R. What about G3? G3 again it is t square, for t is rational, t square also it is for irrational, that means it is a t square for whole R. But what about the G1 function? G1 function, it is taking the value 1 if t is rational, and it is taking the value 0 if t is irrational, right? So now therefore the component function G2 and G3, these are 2 functions are very nice. So that is a differentiable function. But the functions, first component function G1, which is taking value 1 in set of rationals and taking 0 in set of irrational, and you know the first component functions, you can prove it actually. The first component, okay, I have written is small g1, so this should be, I think, say small g1. So this is small g2, small g3, okay, doesn't matter. So the first component function g1t of g is not differentiable at each point. You can prove it. You can prove it for kind of real analysis. That means this kind of functions which is taking value 1 in rational and taking value 0 in irrational, this function is nowhere differentiable. That means you have to kind of, if I want to take about differentiability at some point, you have to take about the limit of the quotients. And since it is this kind of functions, using sequential criteria, you can say that this limit of the quotient does not exist. So therefore it is not differentiable at each point, and therefore my total functions capital G is not differentiable at each point in R, because the first component function is not differentiable at each point. So there you can just use the definitions of differentiability in the real valued functions of real variable as I said. So take a fix a point. So think about the existence of the limit of t approaches to 0, g1t minus g1t naught divided by t minus t naught, and using that kind of the function is defined, g1 is crystal clear, it is taking value 1 in the set of rational and 0 in the set of irrational. Use sequential criteria so that the limit of the quotient does not exist, and hereby the function g1 is not differentiable at each point, and therefore you can talk about the full functions capital G is not differentiable at each point in R. Okay, so this is the algebra of differentiable function. That means if I add 2 differentiable function, it is differentiable. Okay, so take a function f and s, 2 functions. F capital F is a function from set A subset of R to Rn, capital G is a function from A subset R to Rn, or S is an open set. If F and capital G are differentiable at the point T naught, then the sum is differentiable and derivative is nothing but this. Scalar multiplication is differentiable and the derivative at T naught is nothing but this one. Now, there is a kind of another function dot product, that means since capital F is a function from R to Rn, capital G is a function from R to Rn, the dot product makes sense, as I discussed in my last couple of lectures, that there is a dot product between the vectors in Rn, the corresponding if I take x1 x2 xn in Rn, y1 y2 yn in Rn, the dot product means x1 y1 plus x2 y2 up to xn, the scalar product. So, this is also one can check that if capital M and capital G are differentiable, then their dot product it's also differentiable, and derivative you can write in terms of dot product f prime T naught G T naught plus f T naught G prime T naught. There is of course for n is equal to 3, because calculation will be little more difficult. So, for n is equal to 3 I have kind of said that okay, cross product is also differentiable, that means if f is a vector in Rn, G is a vector in Rn, there is a notion of cross product vectors. So, at T naught, if I say that this is a functions from Rn R to Rn, but this function is also differentiable at the point T naught, and also you can have the explicit expression of the derivative, that means f prime T naught cross G T naught plus f T naught cross G prime T naught. I think in my next 2 slides I will talk about the proof of the dot product and cross product. Okay. So, maybe I think in my next lecture I will talk about the kind of proof of the if capital F and capital G are two differentiable functions from R to Rn, then that the dot product is differentiable and you have the explicit expression of the derivative at the point in T naught. And similarly, if capital F and capital G are differentiable at the point T naught, then the cross product is also differentiable. Just use the first principle, just use the definitions, that means you just first principle definition, that means you just try to find the existence of limit t approaches to T naught, ft minus ft naught divided by t minus T naught, and you see that if capital F and capital G are differentiable, then this also differentiable, and not only that, at the end you calculate the limit and whatever limit you will get, and that is the exact form of the derivative. So, that we can see. Okay. So, I think maybe next lecture I will talk about that kind of proof of this very simple proof. You will see it is not at all difficult. Okay. And couple of applications, maybe I will say that once I have the notions of differentiability of vector valued functions of real variable, then kind of certain applications you will see. I think maybe next lecture I will talk about that. Okay. Thank you.